Welcome back to the Latin American webinars on physics. I'm Joel Jones from the PUCP in Peru, and I will be your host today. This is webinar 182, and we're having Nick Kamp as a speaker. Nick carried out his PhD at MIT in the USA, which was followed by a postdoc at Harvard, where he's currently located. Today, Nick will give us an update on searches for physics beyond the standard model using neutrinos. We're very happy to have him as a speaker today. Now, before we begin, as always, let me remind all viewers that you can ask questions and make comments via the YouTube live chat system, and these questions will be passed on to Nick at the end of the talk. So the microphone is yours, Nick.
Okay, sounds good. Let me share my screen. And okay, you can see that all right?
Yeah.
All right, sounds good. All right, well, thank you for the introduction and for the invitation to talk to you today about some work we've been doing. So the title of the talk is Probing New Physics with Neutrinos in Ice, Water, and Rock. And I thought it was well represented by this glacier in Svalbard. So this is the figure that I've been using when I give this talk. But an alternate title could be something like Neutrinos, perhaps a window beyond the standard model. And what I mean by that is that we have observed a very peculiar feature of neutrinos in the past couple of decades. Basically, we've seen that neutrinos oscillate between their flavor states. So neutrinos come in three flavor states. And when we let them propagate over some distance, we see that they switch between these flavor states according to the laws of quantum mechanics. So that's, for example, you can see here the rate of neutrinos from a nuclear reactor measured by the Kamp experiment. So this shows basically their data as a function of the distance traveled by the neutrino divided by its energy. And you can kind of see this wiggle here. And this is what we mean by neutrino oscillations. And so when I say it's consistent with the laws of quantum mechanics, what I mean is that it follows this formula here. So the probability for a neutrino to oscillate depends on this mixing amplitude here, sine squared 2 theta. And this tells you how well aligned the neutrino flavor states are with their mass states. It turns out they're not completely aligned. And then also it depends on this term sine squared m1 squared minus m2 squared times L over 4e, where these m1 and m2, these are the masses of the neutrino mass eigenstates. And then you have this L over E ratio that also appears in this plot. So this is the prediction from quantum mechanics. And if you measure this neutrino oscillation effect, what that requires is that this term here, m1 squared minus m2 squared, is not zero. And basically what that means is that the neutrino mass is greater than zero at the end of the day. And that's very interesting because neutrino masses don't exist in the standard model, sort of out of the box. So already neutrinos are suggesting physics beyond the standard model. If I dive into that idea a little bit more, I show here on the left kind of a depiction from the CERN Courier of the fermions of the standard model. And you can see that most of them have both a left and a right-handed state. So all 6 of the quarks do, and the charged leptons do, electron, muon, and tau. But the 3 neutrinos only have a left-handed state. This is a consequence of the interactions that are in the standard model. There is no right-handed neutrino state. But the typical fermion mass mechanism requires both left and right-handed states. This is via the coupling of each of these fermions with the Higgs boson. So kind of the simplest way to give neutrinos mass is just to add in those right-handed neutrinos. It kind of completes the picture. So maybe it's something that we're tempted to do anyway. And when we add in these right-handed neutrinos, turns out we can more or less explain neutrino masses. And so basically, neutrino oscillations strongly suggest the existence of new particles. And this means that neutrinos are a really well-motivated portal to physics beyond the standard model. They're sort of already heavily suggesting the existence of these new neutrino states. And so that's why I want to talk about them today. And so specifically, I'm going to talk about ways to probe new physics of neutrinos in 3 different materials. So ice, water, and rock. And then there are sort of 3 different ways to use those materials. So we'll start with searches for new neutrinos in neutrino telescopes. And then I'll move on to new detectors that we've proposed to look for neutrinos from the Large Hadron Collider. And then finally, I'll finish up with a new project where we discuss pairing neutrino telescopes with a Muon collider. So let's begin with the neutrino telescope portion. So when I say neutrino telescopes, the detector that often comes to mind is the IceCube detector. This is the longest running neutrino telescope, is perhaps the best way to say it. And it's currently the world's largest particle detector. So it's a cubic kilometer of ice that's operating at the South Pole. And you can see a depiction of the IceCube detector here, where you have basically this instrumented volume of ice about 2 kilometers below the surface at the South Pole. And the detector itself, you can kind of make it out of this image here, but it's basically a lot of these little dots. And each of these dots is one of these digital optical modules that I show here. This is basically a photomultiplier tube within, and some electronics to digitize the signal. And what these PMTs do is they look for the Cherenkov light that's produced by charged particles as they travel through the ice. And so we put about 5,000 of these DOMs within this cubic kilometer of ice, and that's IceCube. You can see kind of a more pictorial description of IceCube here on the left, where you can see the top-down arrangement of these DOMs. And then on the bottom figure, you can see kind of the elevation view or the depth view, maybe. And one thing is apparent right away. There are sort of two sub-detectors of IceCube. There's the green dots, which comprise the entire cubic kilometer. This is sort of the main array of IceCube. But there are also these red dots, and these are indicating the deep core sub-detector. So deep core is a more densely instrumented region of the IceCube detector that's meant to look for neutrinos of even lower energy than the typical, than the kind of the main array detector. And this will be important for studies of things like atmospheric neutrinos, which I'll talk about. So kind of related to that topic, what does IceCube actually see? Well, if we ignore backgrounds and we only talk about neutrinos, IceCube sees two things to first order. We see atmospheric neutrinos. So this is when you have a cosmic ray that interacts in the atmosphere to produce pions, perhaps kaons, and other hadrons. And these hadrons can decay into neutrinos. And so we kind of see this flux of neutrinos coming at us from the entire kind of atmosphere of the Earth. And IceCube sees about 30,000 of these atmospheric neutrinos per year. We also see astrophysical neutrinos. So these are neutrinos created from astrophysical sources, including our galaxy, but also things beyond our galaxy, like active galactic nuclei or blazars. And this was kind of the original goal behind IceCube. It's why you need to instrument such a large volume, because even with our cubic kilometer detector, we see just about 30 of these astrophysical neutrinos per year. So this is really why we needed to go to the South Pole. And these neutrinos show up in a couple of different, what I'm calling event categories. So if you have a muon-flavored neutrino that interacts via a charged current interaction outside of the detector, deep inelastic scattering to be specific, that will create a muon that travels through the detector. We call that a through-going track. If we have a muon neutrino that interacts inside the detector via charged current interaction, you'll get a hadronic shower from the interaction vertex, and then a muon leaving the detector. Usually, we call that a starting track. And then you can also get a cascade. This is a nu E or nu tau charged current interaction, or a neutral current interaction of any neutrino flavor that happens inside the volume, which basically gives you a hadronic shower or a hadronic shower and an electromagnetic shower. It sort of looks like a ball of light. But I think these are better described by looking at actual event displays. So the through-going track is shown here on the left. You can see what that actually looks like in IceCube. So this is a kilometer scale track. Each of these dots indicates photons that are hitting one of our DOMs, and the color indicates the time at which we saw those photons. And basically, we're seeing here a track going through the detector from left to right. In the starting track case, you can see sort of a blob where the initial neutrino interaction happened, and then what looks like a track exiting the detector. And then finally, a cascade, like I said, is just this sort of isotropic ball of light. So what kind of new physics can we look for in IceCube other than these kind of typical neutrino interactions? Well, what we're going to talk about are searches for these right-handed neutrinos that I talked about earlier. And these are also known as heavy neutral leptons when these neutrino states are much heavier than the active neutrinos. And so we'll look for two types of heavy neutral leptons in IceCube. There are what are called mass-mixed HNLs, and these are sort of the typical picture for right-handed neutrinos. You couple them to the standard model neutrinos via mass mixing, and this is common in what's called the seesaw type 1 model. This is sort of the most famous example for explaining neutrino masses from neutrino oscillations. And here we have a couple of different parameters. We have the mass of the HNL, which, as I said, can be much larger than the masses of the active neutrinos. And then we also have the mixing of this heavy neutral lepton with each of the standard model states. So this U parameter here. And then we'll also consider dipole portal HNLs in this talk. So here, instead of coupling via mass mixing, we're saying that the dominant coupling happens via an effective transition magnetic moment. So we have, again, the HNL mass as the parameter, but now instead of this mixing, we have an effective dipole moment coupling the heavy neutral lepton to a standard model neutrino flavor alpha and the standard model photon. And so this is what we're going to work with. And when you, in these HNL models, we have a very kind of unique signature that's possible, these double cascades. So our search strategy is to look for two separated cascades. The first one coming from upscattering. So that's this interaction that you see up here, where you have a neutrino coming in. Usually it's an atmospheric neutrino, and it will exchange some, either a Z boson or a gamma with a nucleus, and it'll produce a hadronic cascade and a heavy neutral lepton. And if that heavy neutral lepton has a long enough lifetime, it will travel a macroscopic distance in the detector before decaying to visible final state particles. So you'll get another cascade some distance away. This is really a smoking gun signature of heavy neutral leptons. And this idea was proposed in 2017 by Colombo and collaborators as a really nice way to look for these HNLs. So we'll start with these mass mixed HNLs that are coupled via these new mixing terms here. One thing that's quite nice at IceCube is that we have new mu to new tau oscillations of atmospheric neutrinos, which give us a source of tau neutrinos. It's hard to get tau neutrinos otherwise, and so it's actually quite hard to probe this mixing U tau n. But in the atmosphere, neutrinos oscillate nearly maximally. Muon neutrinos oscillate to tau neutrinos. So you can see here the disappearance probability, the sort of survival probability of muon neutrinos as a function of their energy and of their zenith angle in IceCube. So -1 here corresponds to neutrinos that are coming through the entire Earth before they hit IceCube, and 0 is corresponding to neutrinos coming from the horizon. And you can see a band here where we're getting basically maximal new tau appearance. And then we can look for these double cascades via these interactions up here. However, what we found when we kind of did our first attempt at this analysis was that this oscillation peak here, it's not at very large energies. It's at around 20 GeV. And it turns out those energies are a bit low for reconstructing two separated cascades in deep core. You can see some details in Leander Fisher's thesis of some nice attempts to do this reconstruction with deep core, but it turns out there's just not enough visible light. It's hard to reconstruct, for example, the decay distance between the two cascades. And you can see it, I think it's well represented by this here. So we have this simplified picture of the double cascades we were looking for, but in a realistic picture, namely in the IceCube simulation, you can see what sort of the best looking double cascade event from an HNL kind of looks like in deep core. You have new tau coming in, produces the hadronic shower and an HNL, and then that HNL decays. And you can see each of these dots is basically one photon detected by one of the PMTs in deep core. And really, we just don't have a lot of light to work with at these energies. Even in the best case, we can only sort of separate the two cascades. And for typical events, it's really hard to distinguish these double cascades from a single cascade. So for the first attempt at an HNL search, we used an alternate strategy we looked for an excess of single cascades over the atmospheric neutrino background. And you can see here, basically the energy distribution of atmospheric neutrino interactions. So these are each of these colors here, compared to what we would expect from the HNL signal. So that's in the gold line here for these specific max and mixing parameters. And we've had to scale this HNL line by a factor of 100 so that you can see it on the figure. And you can sort of already tell from this figure, but this is a very background limited search. It's really hard to look for a little bump in these distributions. We look at more than the reconstructed energy, but in any case, it's hard to see an excess over background. So constraints are really only possible in this single cascade analysis at mixings at the 0.1 level. So that is many orders of magnitude worse than the current constraints on this mixing. So we really need to do a double cascade analysis to be competitive at IceCube. And we're looking into that. So there's possibility for an improved double cascade search with the IceCube upgrade. This is an even denser instrumented kind of addition to deep core with DOMs that are that have better readout capability than the deep core DOMs. And so this might allow us to reconstruct double cascades. We have a grad student at Harvard, Julia Bukmatskin, who's looking into this now. And so that might be an avenue going forward. We can also look at dipole portal heavy neutral leptons. So these are these HNLs that couple to a photon. And again, these also create double cascades. The 2017 Coloma Plus paper actually suggested that IceCube and deep core specifically could set world-leading constraints on this transition magnetic moment to muon-flavored neutrinos. And that's really nice because now we can consider atmospheric muon neutrinos as our source. We're not limited to the 20 GeV nu tau oscillation peak. We can go to higher energies. And so that's what we're doing. I show here some simulated dipole portal HNL double cascades in IceCube, where the green line is pointing to the initial hadronic cascade from the upscattering, and the red line is pointing to the HNL decay to a single photon, so an electromagnetic cascade. And these are events with energies of about a TeV, so kind of much higher than what we were looking at in the mass mixing case. And it gives you an idea of what we can do when we have more energy available. We kind of see very clearly separated cascades. And so we're looking into our sensitivity to these dipole portal HNLs right now. What I'm showing here is the basically trigger level event rates in the relevant parameter space. So this is the HNL mass on the x-axis and the dipole coupling on the y-axis, dipole coupling to muon flavored neutrinos. And these lines indicate where we would expect to see 0.1, 1, and 10 events per year in IceCube, where the two cascades are separated by at least 10 meters, which is sort of the minimal distance that we could ever hope to separate, I would say. And what you can see is that depending on our ability to isolate these double cascades from single cascades, we should actually be able to set world-leading constraints in this parameter space. And specifically, we might be able to say something about a solution to the MiniBooNE anomaly. So this is something that my collaborators and I kind of worked on during my PhD. We proposed a solution to this longstanding MiniBooNE excess, and perhaps you saw Kevin Kelly's lawphysics webinar where he covered the MiniBooNE anomaly in detail, but if not, I encourage you to check it out. But this is really nice. We might be able to use IceCube to make a statement about an anomaly in sort of accelerator neutrino physics. And so the question is, how well can we identify these double cascades and separate them from neutrino backgrounds? So we've been working with graph neural networks to try to do this, specifically this GraphNet open source machine learning reconstruction package. So the first thing that we've tried is to actually reconstruct the distance between the two cascades. And what we found is that it's hard to do that at low energies, so below 50 GeV for the initial neutrino energy. It's hard to correlate the reconstructed separation distance to the simulated or the true separation distance between the cascades. You can see we're not really following this one-to-one line here. But for higher energy events above 50 GeV, we actually start to get pretty good reconstruction capability. So this is, again, suggesting it benefits to be able to go to higher energies. We're also looking at classification, so separating these HNLs from backgrounds. And you can see here just an example kind of PID score separating true HNLs in black from neutrino backgrounds in red, and you can see that also does pretty well. So these preliminary results look promising, and hopefully we can turn that into strong sensitivities soon. We're also considering other neutrino telescopes. So IceCube is not the only neutrino telescope. There are also water-based telescopes, including the Orca detector of Kamp 3net. So this is a neutrino telescope off of the coast of France, which is basically submerged about 2.5 kilometers below the surface of the Mediterranean Ocean. It is a detector that's sort of like deep core in that it's densely instrumented, and it's intended to search for basically atmospheric neutrino interactions. It's a detector that's also under construction. So as of 2024, 23 of the nominal 115 detection units have been deployed. That number is slightly larger now. But basically, this detector is just starting to come online. And the nice thing about water is that we get actually a longer scattering length of optical photons compared to the scattering length in ice. So if we can tell where a photon came from, that gives us a very distinct reconstruction advantage. We can correlate back to the original particle that was produced in the neutrino interaction. And for this reason, Kamp 3net employs DOMs that look something like this on the left, where we have 31 3-inch PMTs in the sphere, rather than just the one that I showed earlier for the IceCube case. We've been looking into the ability to find these HNL-induced double cascades in Orca. Specifically, a grad student in Valencia, Jorge Prado, has been working with GraphNet as well, and has shown preliminary results that suggest the full Orca detector should be pretty good at reconstructing things like the distance between the cascades, the energy imbalance between the cascades, and again, separating the double cascade signal events from single cascade backgrounds. So this is also pretty good preliminary results, and so hopefully should give us good sensitivity with Orca. Now, are there other ways to look for HNLs in neutrino telescopes? Of course, since I have a slide on it, the answer is yes. One thing that we've been looking at with a post-bac student at Harvard, Pablo Castaño, is the prospects of using muon pairs to look for mass mixed HNLs at neutrino telescopes. So what I mean by that is that if we have our IceCube cylinder sitting in the South Pole, we could look for an atmospheric muon neutrino to produce a heavy neutral lepton via upscattering, for example. And then that heavy neutral lepton will decay about 10% of the time to a muon pair, either via a neutral current or a charged current decay. And we can look for basically these two muons passing through IceCube as a very kind of smoking gun signature of muon mixed HNLs. Well, perhaps not smoking gun, but very distinct signature. And we've estimated the global sensitivities of all neutrino telescopes. So not just IceCube, but Kamp 3net, Baikal, and then eventually ones that will come online in later this decade and perhaps in the next decades. And what we're showing here is our sort of preliminary estimate of the global sensitivity from these dimuon searches to heavy neutral leptons. And so I encourage you to focus on the orange lines, which are basically the sensitivities for well-separated muons in these detectors. And what we're showing is what we think we can achieve as far as sensitivity at 2030, 2040, and 2050. So kind of a far future look into the ability of neutrino telescopes. And we're showing constraints or sensitivities in terms of the HNL mass and its mixing to the muon flavor. And what's quite nice is that we're probing a region of HNL parameter space that is in HNL masses between 1 and perhaps about 100 GeV. And this is really complementary to searches that are happening at colliders right now. So the LHC sets the strongest constraints in this sort of higher mass region. But because IceCube can look for high energy neutrino interactions, we are at least we're somewhat complementary and sort of if not competitive with collider bound. So this is still sort of a work in progress, but it looks like an interesting channel to look for these higher mass HNLs in a completely different experimental paradigm. All right, so now I want to switch to the second topic of the talk. So we're going to go to water and rock, and we're going to talk about some new detectors for neutrinos from the Large Hadron Collider. So taking kind of a step back from that, I want to spend a slide kind of suggesting that we're at the dawn of collider neutrino physics. So by that, I mean we are just now starting to look for neutrinos that come from the proton-proton collisions at the LHC. So for example, proton-proton collisions in ATLAS produce a beam of neutrinos that travels sort of transverse to the line of the LHC. And there are a couple of detectors that have started to look for these neutrino interactions. Maybe perhaps the most famous one being the phasor experiment. And so this is a detector that is operating in a very conveniently located service tunnel at the LHC, basically looking for neutrinos and other long-lived particles coming from this interaction point along the very forward direction. And specifically, this phasor detector has a tungsten subdetector, the sort of phasor nu detector, in which they can look for neutrino interactions in the tungsten. And that's exactly what they've done. So phasor has released the first candidates of electron and muon neutrino interactions from neutrinos produced at the ATLAS interaction point. So that is really exciting. It's kind of a new paradigm for neutrino physics. And the one thing that my collaborators and I noticed about a year ago is that LHC neutrinos actually seem to pass through Lake Geneva or Lac Léman, depending on your preference, which is the lake near the LHC. And so you can see a top-down view of this concept here, where we have the neutrino beams from ATLAS, CMS, and LHCb, coming out transverse to the circle of the LHC. And the X's denote the points at which each beam exits the surface of the Earth. And then the pluses show the location where the LHCb beam actually intersects the lake. And if we go to the elevation view on the bottom panels here, you can see for the CMS beam, you can see the point where it exits the Earth. It's about 18 kilometers away from the interaction point. And for the LHCb beam on the right, you can see the point where it intersects the lake. It's about 30 kilometers from the interaction point. And this is nice because it enables the construction of large-scale lake and surface-based detectors that evade muon backgrounds from the proton-proton collision. So this is something that we've been looking into recently, that I've been looking into with my collaborators here. And I also encourage you to check out related independent work from Ariga and collaborators, which came out just around the same time as our paper here. So we're specifically proposing two detectors. The first is the SINE detector, the surface-based integrated neutrino experiment. And here, the proposal is to take standard shipping containers and instrument them with scintillator panels in the front and back, and then arrange them in stacks of 2 wide by 3 tall, and perhaps consider 3 of these stacks, and put them at the location where the neutrino beam exits, the neutrino beam from CMS, exits the surface of the Earth. And what we look for then are upgoing muons from neutrino interactions in the bedrock. So because these are high energy muons, they tend to travel long distances. So we can really look, there's really quite a large event rate of these muons coming out of the surface of the Earth. If we go to the lake, our detector proposal is UNDINE, the underwater integrated neutrino experiment. And you can see a nice logo here from Dia Delgado, former grad student at Harvard. And here we are basically thinking about using the lake as a detection medium. And the kind of initial idea is to follow the concept of the CHIPS collaboration. So the idea here is to basically instrument these 10 kiloton scale water Cherenkov detectors with photomultiplier tubes, and then sink them below the surface of the lake and look for neutrino interactions in the detector. And this is a really cost-effective way to get a large water Cherenkov neutrino detector. The CHIPS collaboration deployed their detector at a lake in Minnesota to look for neutrinos from the neutrino main injector at Fermilab. Our nominal idea is to take 5 of these detectors and put them sort of at the point where the neutrino beam starts to intersect the lake. We're looking for neutrinos from the LHC, so of course we need to compute a flux. Luckily, our friends from Phaser have already done this and have actually provided simulation samples in this GitHub repository here. So what you see is the flux of neutrinos computed from 5 different hadron production models. So we are pairing a model for the production of light mesons with a model for the production of charmed hadrons. And you can see basically all of these models, this is the sort of energy distribution of the neutrino flux. You can see all of the models agree pretty well for the light meson production, but for the charmed hadron production, there are actually significant uncertainties, sort of order of magnitude disagreements between the models in that flux. We can also look at the flux as a function of transverse distance from the beamline, both at the SINE and the UNDINE locations. And what's nice is that because of the high energies here, this beam is pretty collimated. Most of it is contained within a few meters of the beamline, even at the SINE and UNDINE locations. So, you know, we're not losing too much of the flux by building detectors a bit further away from the interaction. We've computed the event rates at SINE and UNDINE by simulating deep inelastic scattering neutrino interactions along the LHCb and CMS beams. You can see here the event rate as a function of neutrino energy at SINE in this top panel and in UNDINE in this bottom 6 panels. And we're showing the rate, both the total rate from all neutrino parents and the rate from neutrinos from charm decay separately. Again, for these 5 different hadron production models. And in UNDINE, we're showing the rate for, so for SINE, I guess I should start with, we're showing only the charged current and mu rate because we need these muons to come out of the Earth. But in UNDINE, we're looking at all neutrino flavors, and we separate charged current and neutral current interactions because Cherenkov detectors might give us some handle to separate the different flavors. So the upshot here is that these are pretty large event rates. So if you look at this table, this shows the number of events that we expect over the course of the high Lumi LHC. And for SINE, we expect about 10 million, for UNDINE in the order of 100,000. So these detectors are really cost-effective ways to collect large samples of collider neutrino interactions. So that's great, but what can we do with, you know, 100K to 10 million, so I'll call it about 1 million collider neutrinos? Well, one thing we can probe is forward charm production in PP collisions. So this is something that's not really well known because it's hard to measure the production of charmed hadrons in the forward direction at the interaction point. But if you increase the rate of forward charm production, that will give you more high energy muon neutrinos in your neutrino flux, as well as more electron and tau neutrinos overall. And so what we've studied is the ability of ratio measurements at SINE and UNDINE to differentiate between these different hydro production models. So specifically, if we measure the ratio of muon to electron interactions in UNDINE, and we also measure the total rate in SINE over the total rate in UNDINE, we find that the different hadron production models lie in very different regions of this 2D ratio parameter space. And so we've computed the expected uncertainty, statistical and cross-section systematic, from each of these predicted points from the hadron production models. And with 1 year of high Lumi LHC data, our 3 sigma error bars suggest that these points are quite far away from each other. So we should be able to distinguish between these different models at the 3 sigma confidence level after about a year of data taking. And this has important implications for things like the intrinsic charm content of the proton, which can affect the forward charm production rates, as well as the prompt atmospheric neutrino flux. So this is the neutrino flux coming from charm decays in the atmosphere. And this is one of the largest backgrounds for astrophysical neutrino searches. So this is really an important measurement to make. But if I turn back to looking for new physics, we can also look for mass mixed HNLs in SINE and UNDINE. And so we have basically 2 ideas to do this. The first is to look for delayed muons with respect to the beam trigger. So I'm showing here on the right, in the mixing versus mass parameter space, the typical decay lengths in the solid lines and time delays one would expect from an HNL decaying to a muon in UNDINE and SINE. Basically, if we can get a time delay of around a few nanoseconds, we should be able to separate that delayed muon from the in-time neutrino signal. And so for masses between maybe 1 and 10 GeV, it seems like we can actually get time delays of about 1 nanosecond or more. And so this is perhaps a good strategy in this mass region. If we go to higher masses above 10 GeV, we now think searches for dimuons might be good here. So again, these are decays via charged current or neutral current mediators to two muons, and we produce this HNL again via upscattering, and then we can look for its decay inside of UNDINE or kind of before SINE. So this is a promising channel to look for HNLs. We are still studying the sensitivity of these detectors to these two channels because there will be backgrounds, and we're trying to do a careful assessment of the backgrounds for each of these strategies, but stay tuned for some sensitivity estimates there. Speaking of backgrounds, one of the sort of most important backgrounds to consider for SINE are cosmic rays. So for those who are sort of familiar with neutrino experiments, you might be thinking it's crazy to put a scintillator detector on the surface and look for muons, because there's a ton of cosmic muons that would be background. So that's true. For SINE, our signal are these upward going muons. And during the high Lumi LHC, we should see those events at a rate of about 11 millihertz. But there will be a background, both from a true coincidence, so a single cosmic muon passing through both panels of one of our detectors, or an accidental coincidence, the two unrelated cosmic muons passing in a short time window. So we've studied this cosmic muon background using the EcoMug software package, and sort of out of the box for both of those background channels, we expect about a kilohertz background rate. So we need some strategies to mitigate that. We've come up with 4, so 2 timing-based strategies using the timing with respect to the initial proton collision, and also the time difference between the scintillator panel hits, and then 2 spatial background rejection strategies. So one with one-dimensional information looking just for upward-going muons, and the other using 2-dimensional spatial information for the front and the back panels. Now, I won't go into detail about any of these just for time purposes, but we have studied, we've proposed some cuts with each of these strategies, and we think that we can reduce the cosmic background rate to below our neutrino signal rate, especially if we have 2D spatial information in these scintillator panels. We're considering a prototype SINE detector, and just as an example, we've taken one shipping crate detector, and if we basically put it at the CMS beam exit point, I show here the number of neutrinos we expect to see as a function of days after deployment. And you can see after about 100 days, which is pretty close to this 3-month window in spring of 2026, we should be able to see a few hundred muons from neutrino interactions, which should allow us, based on our background estimates, to declare at the 3 sigma confidence level that we are seeing neutrino-induced muons after just a few days of running. So that is something that we're aiming for. I want to turn to the last topic of the talk, which is probing new physics, again, neutrino telescopes, but now by pairing them with a muon collider. Again, to introduce everyone to the concept here, I want to show what a typical muon collider looks like. This is from a recent report from the International Muon Collider Collaboration. So we create our muon beam via pi-n decay, and we have a lot of technical challenges to solve before we understand how to inject these muons into an accelerator ring. But once we do, we can accelerate the muons up to high energies and then put them in a 10-kilometer circumference circular ring, which is the muon collider. And here, this is you can get at least 10 TeV center of mass energy for the typical designs of a muon collider, which is great for things like precision measurements of the Higgs boson. But what I want to focus on for this talk is that there's lots of muons here. Per each bunch crossing, so each time muons pass at this interaction point, there are about 2 × 10⁻12 muons passing per bunch crossing at a 5 Hertz repetition rate. So this is a ton of muons. And what you get when you have a muon collider is basically a free neutrino beam with very large quotes around free, because this is an expensive machine in general. But if you build it, muons decay, and that gives you a free beam of these new mu's and these new bars. And so, for example, in this report that I mentioned earlier, they discuss what one can do with this neutrino beam, and what they're showing here is basically the interaction rate of muon neutrinos in a kind of a typical 1-ton detector near the Muon collider for a center of mass energy of 10 TeV. And you can see that that detector would observe an event rate that's kind of way above anything that we've been able to do so far, both in terms of the actual rate and the energy of the neutrinos that we're probing. We're sort of in this collider neutrino regime or even higher. So a lot of people have discussed like what we can do with this neutrino flux and proposed potential neutrino detectors. So back in the early 2000s, sort of when these ideas were first hitting the literature, people considered what one could do with sort of a general purpose neutrino detector consisting of maybe calorimeters and tracking detector near the Muon collider. There's a nice kind of review in this paper here that talks about things like QCD, cross-section measurements, neutrino oscillation measurements that one could do. And then more recently in the literature, we've seen proposals for things like the neutrino slice at the interaction point. So this is basically the neutrino interactions that happen in a detector at the interaction point already. So this is sort of the ATLAS or CMS-like detector that you would build at the Muon collider interaction point. Well, it turns out that detector would see a lot of neutrino interactions already, so you sort of get a quote-unquote free detector here. And folks have also proposed something like a hockey puck detector, where you place a detector at this sort of at a distance from the Muon collider such that you're observing the neutrino beam from both the mu plus and the mu minus beam. And if you do that, you can make really nice precision measurements of electroweak observables. I encourage you to check out actually Adrian Thompson's law physics webinar where he talked about this idea. And what we are proposing to throw into the mix is the neutrino kaleidoscope. So this is the concept here. Oops, sorry. There we go. Is as follows. We consider a Muon collider, for example, at Fermilab, so in Chicago in the US. And if we can point the neutrino beam at one of the existing neutrino telescopes, which I've talked about pretty extensively in this talk, we sort of get a free large detector that we could use to look for these neutrino interactions. And so you can see the concept here. We consider a beam, the neutrino beam from a Muon collider pointed at either P1, which is a neutrino telescope off of the coast of Vancouver. It's a proposal pointed at KM3net, which I've already talked about in the Mediterranean Ocean, or pointed at IceCube, which is at the South Pole. And this actually works because the neutrino beam is collimated pretty well. So over Earth diameter distances, we expect the neutrino beam to be sort of contained within order 100-meter scale distances, which is perfect for gigaton scale neutrino telescopes. It means we can just exactly take advantage of the large instrumented mass without losing flux. So I show here the flux of muon neutrinos as a function of the angle to the center of the beam and the neutrino energy. And on the right-hand side are 3 different axes for how that angle translates to a beam radius at the IceCube, KM3net, and P1 locations, which have, different distances to Fermilab. And even at the IceCube location, which is the furthest away, where you expect kind of the most spread of your beam, most of that beam is contained within a few hundred meters. So it's really within the footprint of IceCube. So that's great. It's an idea that I've been working on in collaboration with Gray Putnam at Fermilab, and we are working on a preprint now, but I just want to introduce the main points of our idea here. There are sort of 2 options to point this neutrino beam from the Muon collider at any of these telescopes. The first is to point a straight section of the beamline at a telescope. So kind of around the collider, we expect kind of a typical 30-centimeter straight section to give us about 5 times 10 to the 14 muon decays per year. If we're near the interaction point, we can actually get a much longer straight section, up to about 100 meters. And that would give us 10 to the 19 muon decays per year, which is much larger, though this comes at the price of a larger angular spread, because near the interaction point, it turns out the beam has to be a bit more collimated, which leads to a bit more angular spread in the muons intrinsically. This strategy is likely only possible for Fermilab to P1, because for KM3net and IceCube, the descent angles are probably much too large to point a straight section. But for P1, it might be possible. Option 2 is to point a beam dump toward the telescope. So we would take a beam dump for the muon beam, and if we send it through a 25-meter decay tunnel, that would give us 2 × 10⁻14 muon decays per year. So comparable to option 1. And here we have a little more capability to point that beam dump toward any of the neutrino telescopes. So this is possible in principle for any of the neutrino kaleidoscope configurations. In both cases, we expect at least 100 million or so neutrino interactions per year in the telescope. So we have a related question: what can we do with about 100 million muon collider neutrinos? Well, one thing we can do is we can look for sterile neutrinos. So sterile neutrinos, for those who have never heard of them, are also just these right-handed neutrinos that I mentioned earlier, but we consider them at the EV scale, so with masses that are a bit lower than what we've been talking about earlier. And this sterile neutrino basically affects the oscillations of these muon collider neutrinos because it would induce a non-standard matter effects as the neutrinos propagate through the Earth. So I show here the equation governing the time evolution of neutrino states. So I show a standard model neutrino, nu alpha, and a sterile neutrino, nu s. And you can see this basically new oscillations that are arising from a new mass squared splitting, this delta m squared 4-1, and the mixing between the sterile neutrino and the standard model flavor state alpha. And that's governed by these theta alpha alpha mixing angles here. And furthermore, there's also basically a matter potential that is visible to the active neutrinos via their weak interactions, but is invisible to the sterile neutrinos, which can create resonant disappearance of your standard model neutrino states, depending on the sign of the neutrino, basically. So what this leads to for our kaleidoscope configuration is distortions in the energy and radial distributions in the kaleidoscope. So in this figure on the right, we're showing the expected event rate for the IceCube and Kamp 3-net configurations as a function of the radius in the larger plot and of the energy in the smaller plot. So the solid lines are showing the standard model expectation, and then the dashed lines show the expectation when you include a sterile neutrino with the parameters that are indicated here. And you can see that disappearance shows up both in the radial distribution and in the energy distribution. So that's a pretty unique effect. We consider a search for muon neutrino disappearance via the sterile neutrino using a kind of TRAX dataset at each telescope. And we perform a 2D energy radial analysis and compute some median sensitivities to sterile neutrinos. And you can see them here on the right. So in the parameter space of delta m squared on the y-axis and the new mixing sine squared 2 theta mu mu on the x-axis, you can see that our projected sensitivity for a typical kaleidoscope configuration is at least 1 to 2 orders of magnitude better than existing constraints, depending on our ability to get a handle on systematic uncertainties. So this is perhaps a really nice way to enter a new paradigm for sterile neutrino searches at the EV scale. We've also considered Lorentz violation. So this is basically violations of Lorentz symmetry, which we all know and love. We learn about in undergraduate physics classes. But it turns out actually many theories of quantum gravity actually predict small violations of Lorentz symmetry, which can lead to frame-dependent neutrino oscillations. So for example, IceCube uses this to look for non-standard oscillations of atmospheric neutrinos with the physical picture that they are perhaps passing through a Lorentz violating field or a field with a preferred direction in space. And the way to describe these neutrino oscillations is with what's called the standard model extension, which was introduced in the late 90s. Here, our neutrino flavor evolution is governed by this effective Hamiltonian, which has these new basically couplings that describe the Lorentz violating interactions of neutrinos. So this A and C. And you can see it has both flavor indices, alpha, beta, but these couplings also have Lorentz indices, mu and mu nu in this A and the C case respectively, which is basically what gives us the Lorentz violation here. So when we look for Lorentz violation in practice, what we can do is look for oscillations over the course of a sidereal day. So here we have the sun fixed in the center of our coordinate system, and a sidereal day corresponds to when the Earth makes a full 360-degree rotation. And because we're kind of pulling back the effects of the Earth's revolution, a sidereal day is about 4 minutes shorter than our typical 24-hour solar day. And so what we could look for in a neutrino kaleidoscope is disappearance in a tracks data set over the course of the day. So here I show the expectation for a small Lorentz violating coupling compared to the standard model over the course of a sidereal day here. And in IceCube, you can see these large oscillations because the baseline is quite long. In KM3net and P1, you can still see oscillations, but they're a bit smaller. However, I will say in the P1 case, because we could perhaps use this 100-meter straight section to boost our event rate, we are in principle sensitive to smaller sidereal variations here. We perform a Fourier analysis. So we basically look for an enhancement in harmonics of the sidereal frequency. So what I'm showing here is the typical amplitude of the second harmonic that one expects just from random fluctuations in each of these kaleidoscope configurations. And then the vertical solid line indicates where that Lorentz violating coefficient would show up, the kind of amplitude of the second harmonic that it would induce. And as maybe you expected on the previous slide, in the IceCube case, we're way past what random fluctuations could do. So IceCube could really severely constrain this Lorentz violating parameter. We translate this sort of Fourier analysis strategy into sensitivities to the Lorentz violating couplings. So here I show sensitivity to two of these CL mu coefficients for the TX and the TY Lorentz indices. And so the 3 sigma sensitivity, which is sort of the vertical dotted line for each of these configurations, should improve upon existing constraints by at least 2 orders of magnitude. So again, this is a nice way to have a new paradigm for Lorentz violation. And just to touch on another point, one can also look for Lorentz violation from higher order operators. So I've been talking about the A and C coefficients, which correspond to dimension 3 and 4 operators. But it's also possible to have Lorentz violation from higher order, for example, dimension 5 and 6 operators, where we have coefficients that are proportional to the energy to some negative integer power. So here we expect basically Lorentz violation to show up at the Planck scale, which would lead to Planck suppressed operators. So for example, in dimension 5, we'd expect operators of the typical scale of 1 over the Planck mass. And in dimension 6, we'd expect operators of the scale 1 over the Planck scale squared. And a nice kind of an important target in this field of Lorentz violation is looking for double Planck suppressed Lorentz violation. So here we have basically we expect that to show up at operators that the scale of about 10 to the minus 38 inverse GeV squared. And what we found with our neutrino kaleidoscope configuration is that if we can boost these muon energies up to about 20 TeV, we can start to constrain Lorentz violation within an order of magnitude of this double Planck suppressed regime. And so we can get pretty close to these quantum gravity motivated regions, which is a really nice motivation for these neutrino kaleidoscope searches. So just to conclude, I've talked about many different ways that we could probe new physics in the neutrino sector. We've talked about new signatures. So IceCube and KM3net are looking for heavy neutral leptons with a double cascade signature. New detectors, SINE and UNDINE, which have been proposed to detect large numbers of LHC neutrinos, which can constrain things like forward charm production, but also potentially heavy neutral leptons. And then also new beamlines. So we've proposed neutrino kaleidoscopes, which pair neutrino telescopes with muon colliders, giving potentially strong sensitivity to non-standard oscillations from things like sterile neutrinos and Lorentz violation. So thanks for your attention, and I'm happy to take any questions.
Super. Thank you very much for the very nice and comprehensive talk. So the session is open for questions from the rest of the organizers. So if anybody's got a question, please go ahead. Okay, I'll start. So regarding, where do I have this? Okay, so regarding SINE and UNDINE. Okay, so the first one is just a curiosity. Can you go back to slide 24?
Sure.
So
It's a bit of a lag. There we go.
yeah, there you go. So this is just a stupid question, but the neutrino beam on the bottom right seems curved.
Yeah, okay. So this is because this is from the curvature of the Earth.
That's
What
what
we're
I
plotting
thought.
here is that, yeah, exactly. Yeah.
So in principle, yeah, so the distance is that much that you can actually notice the curvature of the Earth, and you're just flattening it, and the consequence is that the beam curves.
Exactly.
Okay,
Yep.
okay, great. I was just surprised by this. Okay, anyway, so the serious question. So regarding your background reduction for SINE, you say that you plan to use timing with the LHC collision. So that means that you need a precision that is good enough to differentiate between each bunch crossing, right? So that tells you there's like 12 nanoseconds between each bunch crossing, right? So if you have collisions every 12 nanoseconds or maybe it's a bit more, but it's of the order of 12 nanoseconds, right? How do you plan to probe heavy neutral leptons, right? Because if you want them to be long-lived, they will be moving slower than the neutrinos. So I was wondering if it's a long distance, right? So I was wondering if you'll be able to actually probe these heavy neutral leptons. I mean, I was wondering if the timing would just block any signature of a heavy neutral lepton.
That's a good question. So we basically have a kind of sweet spot that we can look for. Let me pull up a backup slide. So you can see here. I think our understanding just is that the bunches are spaced by 25 nanoseconds at the LHC. And what we expect, so these figures here are showing the timing distribution of the standard model neutrino interactions that we expect. So basically the muons from kind of time of or speed of light arrival. And they're all contained within a few nanoseconds. So basically the delay window that we can look for is somewhere between a few nanoseconds and 25 nanoseconds.
Right.
So yeah, if the delay is longer than that, then we can't because we can't look for it. So we'll see where in parameter space that leaves us, but we kind of think between 1 and 10 GeV, there is a region where we get a few nanoseconds delay that we could potentially look for.
Right. Yeah, the 12 nanoseconds I was thinking about was for searches at the LHC. So given the 25 nanoseconds, you were restricted to delays of 12 nanoseconds, right? So I was wondering, right, if you have it even longer distances, but okay, you see, you have it there. It's 2.5 nanoseconds. So then that means that they must be very light, heavy neutrinos.
Well, it depends. I mean, it's a combination of the, I mean, it's mostly dependent on the mass, but in this, see if I can get there. It's probably easier if I do this. In this figure, you can see even so HNLs that are between 1 and 10 GeV, if the mixing is somewhere around the 10 to the -5 level, that's where the red dashed line is suggesting that we get timing delays of 1 nanosecond. So they can still be pretty heavy and give us a nanosecond level because it's kind of a convolution of even if it's moving slower when it's at heavier mass, but the decay time is much shorter, so you can still get like that can correspond to at the end of the day like just a few nanosecond delay.
I see. Okay, cool. I don't know if there's any other questions. I have more, but I don't know if
I have
yeah, go ahead.
a naive question for Nicolas. So, first of all, very very nice the talk, and also I like it the last slide with the sign that is there. No, yes. Let's get it from the poster. No, but I was wondering what would be the capability in the case of, because there are some extension in the case of extension of the standard model with extra fermions, that it could be possible to have charged fermions that are kind of partners with the heavy neutrino. In the sense, is it possible to would be possible also to have sensitivity to, instead of producing a heavy neutral fermion, a heavy charge fermion that at the end is kind of similar because of charge conservation?
Yeah, I mean, so you're thinking about like C-slot type 3 type models or something
For
like
instance,
that?
or
Yeah.
the ones that you have like SU2, right? Kind of you have four
Yeah, the right
family
lamps
or
symmetric,
something like that, yeah. Without
Yeah, I
extra,
see.
yeah.
I mean, in principle, yeah. I mean, I'm not so familiar with the phenomenology of these models, but I guess I think in any of these strategies, it should be perhaps also possible. So is there one of the experiments that you're thinking of specifically for these charged neutrino partner states?
I mean, I guess for the energy scale, I would say that with the Muon collider, because at the end also well, I mean, also it would produce neutrinos at the final stage of the production. Let's say that.
Yeah.
Instead of the neutral neutrino goes from the muon, let's say, you produce there a charge fermion, and then it decays and produces neutrino at the end. So
yeah, it would be interesting to study. I suspect that we could probably probe these things, especially, and also one way to like in this talk I've been talking kind of extensively about these upscattering based ways, like you have a neutrino that upscatters into a heavy neutral lepton. But I think in principle you could also upscatter into these like these additional charged fermion states. And I think you could use some of these same strategies. So even at this muon collider configuration, one thing that we want to look at is rare neutrino interactions. It's a little difficult because the telescopes are kind of coarse detectors. It's hard to look. The only new signature that one could look for are muon pairs, we think. But if the new charged fermions decay to dileptons, I think there could be some sensitivity there, which would be interesting to estimate.
okay, and just a very small, like also naive question. In the case of the kaleidoscope, also would it be possible to point to other kind of neutrino experiments that are not kind of telescope, let's say super Kamiokande, something that are more with a smaller form factor for the energy scale of the neutrinos, let's say, because there the full stuff it will shine with signal. I would, I don't know.
I mean, I think so. And I mean, from our discussions with the accelerator physicists, all we care about is whether we can point the beam in an arbitrary direction. So I'm sure you could also point it at super K, or for that matter, hyper K at these time scales. So it would be that's also an interesting thing to investigate. We chose neutrino telescopes just because they're the largest, and you're already at a TeV energy, so you're kind of well within the like detection capability of a neutrino telescope. But you could also do hyper K.
Okay, thank you.
Super. For a moment, Roberto, I was thinking you were talking about long-lived charged heavy leptons, but those would be ruled out by these long-lived particle searches,
Yeah.
at the collider itself, I guess. Any other questions? Let's see. I'll go for my next round of questions. So, regarding so on your slide 17, you put constraints on the dipole operator, right? And then what it confuses me is that you're putting constraints on the new mu, right? But in this kind of interactions, you are a flavor blind, aren't you? Because this is a neutral. You are not producing a muon anywhere. So I guess that the constraint is considering only, I mean, you're putting new mu because you have you're considering a new mu flux from atmospheric neutrinos or something like this. I mean, can you actually distinguish the new mu, new e, new tau dipole couplings for this kind of searches, or what's on your mind here?
No, you're right. They're flavor blind. So I show the muon couplings because we get mostly muon neutrinos from the atmospheric flux. That is true. But you could also, in principle, set constraints on the other flavors. So there's also pretty sizable electron neutrino flux from the atmosphere. We will also probe those flavor dipole moments. So the original Coloma paper suggested doing this for dipole couplings to tau neutrinos, but then you also have to use the oscillated taus and you're at lower energy. So.
Okay, super. And regarding your neural network, can you actually distinguish the dipole interactions from the standard seesaw decays? Because
yeah, it's a good question. My guess is no. So the most common decay channel for the seesaw HNLs is at least at the masses we're considering, you usually go to a neutrino pi naught. So, the decay is effectively to 2 photons versus 1. There's no way we can tell that apart in IceCube. The difference might be in the correlation between the kind of the distribution of decay lengths and energies of the 2 cascades. So that will look a little bit different in the mass mixed case versus the dipole portal case. We haven't done a careful study of differentiating between the two, but it would something to look at.
Fantastic. Okay, we haven't got no questions from the audience. I don't know if there's any other questions here from the coordinators. So I have one last question, which is regarding the di-muon proposal for in IceCube. So here, what the idea is that you have, say, an atmospheric neutrino, produces a heavy neutral lepton, and then the heavy neutral lepton will decay into the purely leptonic channel, only into the 2 muons, and that in principle is something that you can tell apart. So in these curves, are you considering the initial shower from the production of the heavy neutrino? Does that help, or does that actually play against you?
Yeah, so it sort of depends. In these curves, we're not considering it. So we're considering upscattering sort of anywhere within or around IceCube, and we just care that the 2 muons have at least some minimum separation when they're inside the detector. But one thing that Pablo has also been looking into are these are interactions where you kind of have this, it's like the double cascade signature, but now it's like a displaced vertex where the HNL is long-lived enough that you have the cascade, and then you have the decay to 2 muons a little bit further away. And that is nice because I think it's better motivated as a low background channel. If you have a cascade and then a separated muon, you can't really do that in the standard model, whereas there are standard model ways to produce dimuons. So we're looking into that too. And that might also be interesting. We just haven't done a very careful estimation of the event rate yet.
Okay, great. So I guess that's it. So thank you very much. Yeah, we're running out of time too. Thank you very much, Nick, for the wonderful talk and the great answers. So before we leave, I'd like to remind all of the viewers that next week we have another webinar, right? This time will be by Javier Berto, and please be there. So thank you once again, Nick, and we'll be seeing you around.
All right, thanks for having me. I appreciate it.
Bye all. Okay, we're offline. Super. So